Why don't we start now? I want to introduce Karl Havlak. Karl has been involved in a number of things with Symbiote, and he and I have a water apparatus device that we built each, but can never get it to work, or we don't pay attention to it. But this is on a totally different thing, and I love talks that involve random stuff. So Karl, take it away.
Well, thank you very much, Brian. I hope I don't disappoint on the random part, because it's sort of pseudo-random at the end of the talk. But I do thank you for allowing me to give the talk. I thank all of you that are here to watch. This is a talk on a very common topic, very well-known topic, Lotka-Volterra model. This is a result of a student project that was funded by our university Faculty Learning Commons on a mini grant. And basically, it's a one semester project where the student is encouraged to just take on something and see where they can go with it, with some guidance from a faculty mentor. And so I was the faculty mentor. This wasn't really my area of expertise as I went through, my undergraduate training and graduate training, but I'm very interested in modeling. And so we just tried to see where we could go. Hopefully we didn't do anything too unconventional in what we've done here. If any of you are experts in this area, you feel free to give us some hints on what you think we should do next. But I just think it's a great example of turning a student loose, and here you have a model. What are you going to do with it, and how can you get some data and figure things out for the model? Now, I hope I'm still live. It looks like Brian's frozen on my. Oh, there he is. Okay.
No, you're fine.
Okay. You were being very still. All right. So anyway, this is the Lotka-Volterra model. It should be familiar. I'll give a quick overview of that. Lotka had a model that applied to chemistry in about 1910, and used the law of mass action, which is about chemical reaction rates. And then in about 1925, Volterra took that idea and applied it to predator-prey populations. So this is a model that's almost a century old as far as being applied to predator-prey. But the standard assumptions, briefly, you have a predator and prey system where the prey will grow without bound if there aren't any predators around. And that's a pretty wide assumption that there's enough food, there's nothing restricting them, so they grow. The predators likewise depend totally on the prey, and so if the prey aren't there, they will decline to extinction if you let the model run without prey involved. And then there's these interactions between the predator and prey. They're free to roam. It's equally likely everyone runs into everyone else in this system, but those interactions work to the detriment of the prey and to the benefit of the predators. And so you get something like this, a standard predator-prey model, where you can see, are you able to see my hand icon?
Oh, yes.
Okay,
yes.
Great. So you can see that the exponential growth term here for the prey population, you see the decline term for the predator population, and then these two mixing terms, the interaction terms, working to the detriment of the prey and to the benefit of the predator. And you have these unknown constants. And that's sort of was the first focus of this model was, okay, we've got these constants, what do we do with them? How do we get the constants out of there? And you can make up constants and see what happens, but not any four constants will suffice. I mean, you can't just throw numbers in and hope it works out. So if you judiciously pick some constants, here's a sample, you get this hopefully intuitive sort of result from the basic model, which is you see the prey, which is the blue graph, they'll grow sort of unchecked until the predators start getting, there's enough predators around where then you'll start seeing a decline in the prey. And at some point there are too few prey around so that the predators reach a peak and they'll start declining, but then there are too few predators around, so the prey will start growing again. And you see this cyclic behavior where these offset peaks, the prey reach a peak, and then shortly after that, the predators will reach a peak, and you just see this cycling back and forth. And this would be obviously an idealized situation, doesn't take in any account for year-to-year changes in food availability or weather changes or whatever. But like I said, it's sort of an idealized situation. And so our goal was to try to find some data to find these constants for that and see how well it works for some real world data. Now, one of the standard examples that's given in a lot of textbooks is this hair lynx from the Hudson Bay Fur Company data. And in researching that data, it's some sources sort of see it as suspect because this is only on the furs that were harvested. And, you know, from year to year, it may be that the lynx was more popular and harvested more and so forth. Plus, we couldn't find the actual data, and we didn't want to approximate data by kind of looking at the graph and guessing what they were. And so, you know, it's probably a good sampling, but the nice thing is you do see those peaks and they're sort of offset. So it sort of suggests that the model at least has some reality, although the peaks are higher and lower in one year from the next. So we were hoping to find a better data set to compare or to use for the project. Well, in searching, we found some data by a group, Blasius and friends. They were trying to, it was called, the paper was entitled Long-Term Cyclic Persistence in an Experimental Predator-Prey System. And so what they did was they were trying to show this predator-prey relationship, this cyclic relationship, seeing if they could demonstrate that it would exist in sort of an idealized situation. And so they had a planktonic system, which consisted of algae and rotifers. The algae are the prey in this, even though it's a plant, they're the prey, and the rotifers are the predator in this situation. And so they put them in a chemostat and let them grow, and every 4 days they'd go in and collect the data. At least in this particular data set, there were 10 different data sets, and we picked the one that looked most likely like the cyclic behavior that we were hoping to see. And you can see, even in their idealized situation, there's some chaos here at the start where things are kind of jumping around, but it does seem to settle down into sort of the typical pattern that you'd expect from at least the model that we have. And then towards the end, not sure what happened, but something sort of broke down there towards the end, and the cyclic behavior sort of goes away. But we decided this was a good data set, I mean, visually, and we had the actual data that we could put into an Excel sheet and look at. But we didn't like the whole data set. And we were wanting to estimate the coefficients. We weren't necessarily just trying to model this behavior that we're seeing in front of us, but we wanted to get a good set of coefficients that would reflect the predator-prey model that we sort of expect from the Lotka-Volterra model. So we narrowed it down. It looks like sort of the middle section of that data here towards the middle, from about day 21 or so, day 20 or so, to a little over day 100. It looks pretty, at least it sort of has the dynamics we liked. And so we thought that it would be best to narrow it down, just to have a data set that's displaying the cyclic behavior that we wanted, to give us a good shot at getting estimates on what those coefficients might be. And so that was the data we used. Like I said, there were 10 data sets, and we sort of filtered through them and came upon this for our model. So we started with A and C. So the way we did this, we didn't want to just start plugging in X's and Y's, predator numbers and prey numbers, and then solve systems of equations, because the dynamics, we didn't feel like it was going to capture the dynamics. I mean, if I picked places where the predator where one of them was reaching a peak, you would get maybe 0 as on this side every time. And so it seemed like you could strategically pick values that might give you any kind of A, B, and C and D you wanted. So we thought a better approach is try to use the features of the cyclic behavior. And so first thing we did was, well, let's pretend there was no interaction. And so looking back at this data, that's best described for coefficient A, this would be the exponential growth term. That's best described when there's very few predators around. That would be the place where we'd expect at least to have the most representative exponential growth portion of this. And you can see it at these low points where the predator at low points, you see a large jump in the prey. Here's another one where the predator is at a low point, you see a large jump in the prey. And all the way through here, that happens. And so we felt like, okay, there are predators around. They are still restricting the growth somewhat, but this would be our best estimate for would need to be. And then in a similar way, when we look at this other term, this other equation with no interaction, to estimate the decline in the predator population, well, same thing. We felt like the best way to figure out the decline was when there were as few prey around as possible. So at the bottom with these low points for the prey, you can see that's where we start seeing these larger drops in our predator population. So here's a low point, you can see a large drop. Everywhere there's a low point, that's sort of where those largest drops occur. And so we use that. In our model, we decided we would go with those low points and high points to get a good estimate on A. So if we solve for A in that first equation, then we simply take our data and use a divided difference. And here's just a particular data point that we used, or 2 data points, to get an estimate as to what that coefficient for A should be. Did the same thing for C. So that's our growth and decline coefficients. And then we did it for every single one of them and got a mean value for the A value and the C coefficient. And we went ahead and calculated the standard deviation from the data set we had to use later in our pseudo-random process. So if we've got A and C, next are the interaction terms. Once we have A, we just put it back in, solve for B, and same way here. And then we're at the same dilemma. Do I just go through and start plugging in all the values to get an estimate for what B should be? Should I go ahead and plug in for D as well? And so this one was a little tougher to figure out what we might do because this is the interaction. And so we wanted to try to figure out in the data where the interaction might best be displayed. So visually, we felt like the interactions are where the predators are increasing the most and places where maybe the prey are decreasing the most. That sort of might capture the dynamics of where those interactions are being most highlighted through the data. So that's sort of what we did. I say sort of because these terms, they were very picky in terms of our final model later. But our first pass through is we just said, okay, where we see a large increase in the predator, well, that's where the interaction is really being seen, or a large decrease in the prey. That's where there's some strong interaction term is being highlighted. Anyway, doing that, using the data, again, using divided differences and the values we've already calculated for A and B, you can see we got these coefficients, much smaller coefficients. And so they're a little more sensitive as far as how closely the data was actually measured to begin with, those sorts of things. So, I don't know how they counted the algae or how they counted the rotifers that were in this system, but this is what we have. And using these coefficients, then we get this Lotka-Volterra predator-prey model for this particular data set. And so then we crossed our fingers because we had no idea whether we were going to get it. Like I said, you can't just randomly pick these things. The model will crash on you very quickly if you don't pick them right. And so we crossed our fingers and hoped that we'd get a model that at least made sense. So running some MATLAB code, it at least gives us it is a valid looking model. I mean, we have predators and prey, it's at standard, peaks that are offset. But then the obvious question is, how does it compare to the actual data set? And so the model, this is for the prey, and it visually looks pretty good. When you're looking at the extent of these peaks and valleys, it's doing a good job, except if you look at these peaks in the model, they are drifting a little so it's not quite capturing the period of this cyclic behavior. So there is some drift there, which we had a hard time ever getting straightened out. But it looks like it's doing a decent job. I mean, there are ways to test it with, taking our data and comparing it to the model, but numerically to see how well it's going. But we sort of visually said that looks okay. We're actually very happy. Those were the first coefficients we came up with. We didn't even try to refine them when we saw this one. This is for the predator population, and it starts out decent. But as you can see, the data for the predators is not, there is some drift northward here. That they're getting higher and higher, these peaks. So there's something going on there with the rotifers that, this is not a perfect Lotka-Volterra system that we're trying to model. So yeah, it makes sense that we wouldn't be able to capture this drift because the Lotka-Volterra model doesn't have that built into it. So that was a good, took us a good part of the semester. Like I said, it's a 1 semester project, and we got to that point. So the question was, what do we do next? Do we want to go back and try to get better coefficients? Or do we want to try what we'd originally said is we want to capture, we knew there was going to be this variation in peaks and in valleys. Is there a way to capture that with the Lotka-Volterra model? And so we came up with a different scheme for using Lotka-Volterra, but numerically letting the coefficients vary. So we call it a pseudo-random model because it's not totally random. I mean, it is in a sense that we're picking random coefficients, but what we're doing is we fix a time step. The data was actually every 4 days, but we tried different time steps of every day, every 10 days, 20 days, just different ways to modify to see if we were going to be able to capture the dynamics. And then what we did was we randomly selected the coefficients at each time step. So on day 0, day 4, day 8, or whatever time step we'd set. And the way we did that is we had those means that we calculated that we felt were doing okay, those means values for those coefficients. And then we took an interval around that coefficient that was equal to twice the standard deviation. So 2/3 of the time we should be landing, basically 2/3 of the time, the coefficient should be within this range of the values that were in the data set. And then we randomly selected a coefficient from that interval. Now we did it both by a uniform distribution. So we uniformly distributed where you just picked them randomly from one deviation to the left and right. And we did it with the normal distribution where it was more likely to pick the value closer to the center. And then for A and C, for those exponential growth and the other coefficient, the decline coefficient, it worked okay. But it turns out the B and the D, that is the mixing coefficients, the interaction term, we had to really, we weren't able to go with just a standard deviation. We had to go half a deviation or even a quarter of a deviation because it was very sensitive to those particular values and our model would crash. But doing this by picking these random, resetting the coefficients at each time step, so we're sort of modeling change from time step to time step. In a real world situation, it'd be like change in food availability or possibly change in climate or something like that as the system goes. And so this was we had a scheme for saying what was a good simulation and what was a bad simulation. So this came out, and I'll explain what those were in a minute, how we designated that. So this was one that was a good simulation, and we picked one that looked really good whenever for one to display here. But this is a good one. You can see again, the peaks aren't lining up perfectly. There is our blue graph here is drifting on us a bit, but overall, it seems to be, this could be a reasonable output from a predator-prey system. It's not that much different than the one the actual data had. Here's one that's a good predator simulation according to our naming scheme. Again, the data is sort of drifting northward on us here, but our model is, again, here in this area, it's a lot lower than the rotifers were. So, maybe the rotifer predator prey, we should have maybe started in this area for the data instead of using all the data, but this is what we went with. And then we had some that were bad. I mean, this one visually is obviously bad. The predator, this is the prey, seem to be getting out of hand. Here's a predator simulation that's we considered as bad by our scheme. And so here's what we did. So we set our parameters. We had messed with the time step. We messed with the standard deviations interval on our coefficients. We also we checked where those peaks were occurring. So if you look at the data, the peaks are approximately every 10 days, there should be a peak. And so we checked that if our output had a peak about every 10 days, we counted that. Okay, that's a check mark. We didn't want the highest peak of either the predator or the prey.
Karl, I'm just giving you a heads up, like I'm doing with all speakers. We've got about 5 minutes in our allotted time. Go ahead.
I got about 4 minutes, 59 seconds left of talking. So we're good. The other thing we looked for were the highest peak. We didn't want it to be more than a 25% higher than the maximum peak in the data. So we didn't want it, we felt, and that was randomly chosen. We played with that number as well. Sometimes we did 10%, sometimes we did 50% to just see what would happen. So we tried to keep our outputs within 25% of the highest peak. Also, the lowest peak, not the valley, but the peak, we didn't want any of our outputs to be lower than the 25% lower than the lowest peak. So looking back, you can see this one's failing probably because our lowest peaks here are lower than this lowest peak that we're seeing here. I mean, that's the lowest peak in the data, and we've got our low peak too low. So that one didn't meet the condition. The same way here, this one is probably failing because our maximum peaks are way above, more than 25% above the maximum peak. So by this scoring system, running these simulations 10,000 times with each set of choosing random coefficients, where sometimes we played with the time step, sometimes there was a lot of different variables that we were trying to tweak to see how it was going. And so we kept a score, and we said a model was good if more than often than not, more than half the models would come out to be what we would say is acceptable. And that didn't happen very often with the values that we had for our coefficients. And let me explain here in the results. First of all, we needed more time. It was a 1 semester project. Once we got to this pseudo-random part of the project, there were just so many different variations we could try. We were having a hard time getting a systematic approach to it, and that was our issues. We weren't sure how to systematically say, okay, let's use this time step along with our intervals of this length, along with a 25% gap as far as saying it's a good model or a bad model. And then it turns out that it's very, very sensitive to that B and D coefficient, that mixing coefficient. They were very small to begin with, the numbers were. And so we had to pick intervals for B and D that were not very big intervals. We were almost picking the B and the D value in our model. So we sort of ran out of time. I don't have a final result to say, here are the coefficients that are the ones that you want to use. It was more about the trial and error to see where we got and give the student an idea of, how are you going to analyze? We've got this model. What's our analysis going to be? So the final conclusion is it really was a lot of fun. We just played with it. I'd encourage you, even with this data set and this model, I would encourage you to think about giving a student this problem and see where they go with it. Anyway, that is the conclusion of the project. Thank you very much.
Well, thank you, Karl, very much. Any comments? Feel free to just unmute and speak up. I know we have about 37 or so people in the room. That's a lot. But...
Yeah, Karl, great project. Very, very interesting. I was just curious how the coefficients from the pseudo-random process compared with those that you initially selected by picking choice points along the plots.
Yeah, so they were based on that those coefficients we found were the center of the interval that we were sampling from. But it turned out, just by the way created those coefficients, the A and the C were going to be too small to begin with, because we selected those as though that was exponential growth, but there were still predators there. So it was slowing down the growth. So the A is obviously smaller than it should have been. The B and the D, the mixing coefficients, those we probably should have gone back and tried to get a better estimate by maybe using more data points or something, because there were very few times we'd get successes by having any interval about those coefficients.
I see. Thank you. Yeah.
Any other questions, comments? I think the last point is that it's a lot of fun, because the students see in the uncertainties of modeling and the very demanding efforts of parameter estimation, a lot of creativity. Why don't we try this? Why don't we try that? This is a complex model because it is not physical in the sense of a pendulum or something. And so when you get into these, it's certainly not human interest, but biological models don't always have perfect fitting parameters. Oftentimes faculty will take data from a physics experiment, which is concrete, F equals ma, and estimate parameters there first time through. And but eventually you want to bring what Karl has brought to the class, namely the ambiguities of how on earth would you get these numbers? And those numbers have meaning. They have predation rate has units, has meaning. And then the students begin to realize, how many rabbits per day can the fox eat? How many slices of pizza per day can a dorm resident eat? And they begin to get a handle for what's realistic numbers. And then out what is a reasonable number. And I love the spread you offered. Look, let's take the starting one and just play around with, I think you said something like 10,000. And of course, being of a certain age, doing 2 or more would have been traumatic, but doing 10,000 is very easy now, and then analyzing those results. If there are no more questions, this will, of course, be recorded, and Karl has provided the references, which we put up there as well. So you can look that up and be in touch with him if you wish about a project. And I think he's hit on the spot. There's never enough time. I think that's right. So thank you, Karl, very much.